Okay, thank you, Sonal. I just wanted to say thank you to the audience. It's a pleasure to be able to present in front of this esteemed group of surveyors and mappers. It's a treat to be able to speak to you all today. I'm going to talk a little bit about a technology that some of you may have heard of, many of you probably have not heard of. It's known as laser triangulation. And I'm calling it a high-resolution companion to LiDAR. Sometimes in industry we have a tendency to say this technology is better than that technology, but what we've seen in the industry is that this technology complements LiDAR quite well. And I'm going to talk about why that is. First and foremost, though, I'm from Pavemetrics. We're a spin-off of Canada's National Optics Institute, or INO. And we specialize in the development of high-speed 3D scanning systems and algorithms for analyzing the data from those systems. And the purpose of those systems is really high-speed infrastructure inspection. Our technology is used in more than 35 countries around the world to scan everything from roads to airport runways to railways and tunnels. And around the world, we're really well known for pavement condition measurement. In fact, our 3D technology is the most widely adopted technology of its kind. In the United States, 40 out of 50 state departments of transportation rely on our sensors for pavement condition measurement. Here in India, a recent project by one of our customers, a company called Ramdas, who takes our sensors and integrates them and deploys them. They supplied 2 pieces of equipment to the Tamil Nadu State Highway Department, and those projects were used to scan 45,000 kilometers over a period of 3 years. And that data is used to help program properly roadway maintenance to get the biggest bang for the buck when it comes to which roads to treat, how to treat them, and when to treat them. Okay. So the presentation today is going to largely focus on technical matters, and I'm going to include a discussion of LiDAR and some of the comparisons and contrasts to LiDAR, and we'll wrap up with a bit of a discussion about how we map this data and correct the data for geometry. But first I want to talk about accuracy, because anytime you get into discussions of technology, there's at least 2 camps. There's one camp that says, gee, that's not enough accuracy for me, that doesn't do what I want. And then there's another camp that says, that's way too much accuracy, I don't need that kind of accuracy. Okay, so how much accuracy is enough? Well, let's give an example. Let's say you've designed a road, and it's a mile long, and it's about 28 feet wide. Okay, it's 2 lanes of traffic. And you're going to put down 3-inch asphalt surface, which is 76 millimeters. And let's assume, for the sake of discussion, that asphalt costs you $75 a ton. That's a fairly current number in the United States. So if you do the math on this, you come up with something like 2,700 tons. In fact, it's 2,772 tons. And that's a cost of almost $208,000. Okay, so you hire a contractor to go out and they put down asphalt. And they put down a mile of it, like the design says, and they put down 28 feet wide amount of it, like the design says, but they add on 4 millimeters of asphalt. 4 millimeters is not very much. Asphalt's still $75 a ton, but now you need 2,917 tons. And you've got $11,000 of extra cost on that 1 mile due to 4 millimeters. There's a lot of other reasons why they could have used more than 4 millimeters. They could have gotten the width wrong. And let's face it, usually you're not paving 1 mile. Usually you're paving thousands of miles or thousands of kilometers. So it adds up. It gets into the millions and tens of millions very quickly. Looked at from another perspective, though, sometimes not enough material is put down. And the research says that just a 10% under thickness in a concrete road will reduce the life by 90%. So if you don't put enough material down, ultimately it's going to cost you anyhow. It's not going to perform as planned. Okay? So accuracy matters, and it usually does come down to a few millimeters. Okay, so let's talk about laser triangulation now. These are the sensors in question. They're about 10 kilograms each. They're the size of a tower desktop computer. And I'm going to bring up a few bullets. I'm not going to cover all these, but I want to highlight a few items. This is a sensor that you can mount on a vehicle and drive down a road or a runway or a tunnel or a rail at 100 kilometers an hour. It can be used day or night. It has its own built-in lighting system and can provide resolution up to 1 millimeter transversely and 1 millimeter longitudinally. So imagine a wireframe model dropping onto the surface you're scanning. It's 1 millimeter by 1 millimeter. And the vertical accuracy of each of those points is 0.5 millimeter. And the system captures both a high-resolution digital image of the surface as well as that 3D model. And so here's our wireframe model. You can kind of imagine the system in action. Okay, so let's talk about laser triangulation and how that actually works, what we're actually talking about. So we're using trigonometry to solve this problem. We have a line laser that's projecting a laser onto the surface. We have a surface that's reflecting the light back up to a camera. Well, we know the spacing between the camera and the laser. We know the angle with which the laser beam was emitted. We know where the light hits the imaging sensor, and from that we can then derive the angle, and ultimately we can then solve for X. We can recreate a 3D model of that same surface. And so what actually happens is we project a laser line onto the surface between 5,000 and 11,000 times a second, and we have a synchronized camera that takes a picture of that laser line. And it's by analyzing the shape of the laser line that we're able to determine various features about the surface. So we get a picture of the surface and we get a 3D model. And you can see in this illustration, if we had a perfectly straight line, you'd have a perfectly flat surface. That never happens. There's always things like macro texture of the surface. In this case, there's a bunch of cracks in a piece of asphalt. Okay, so we're just a sensor company. We don't do data collection. We don't build data collection vehicles. Our piece of this puzzle is the things in red. The rest of the solution is something that our customers do. They supply a chassis, they build a sensor mount, they install the sensors, they add on GPS, they put on an optical encoder, a DMI, to give linear distance. In the rear of the vehicle, they have a small computer rack. These are industrial rack mount computers. The white box is a sensor controller. Underneath that is a computer with removable hard drives, about 1 terabyte or larger each. And then on the bottom is a UPS. The yellow thing is a power inverter that takes power from the alternator and supplies it to the system. And then up front you have an operator station. So this is pretty similar to mobile LiDAR. Anyone that has seen a mobile LiDAR system, they know it's something like this. How you mount the sensors is a little bit different, but the stuff inside the vehicle that controls everything is pretty similar. Okay, scanning procedure. So we've got our laser diagram back here. As the vehicle moves down the track in this case, the position of that laser line is going to move from left to right. And as that laser line moves, that's how we scan the surface. So 5,000 to 11,000 some odd times a second, we're pulsing that laser, but in reality what we do is we stitch them all together. Left and right lasers in each successive scan. So one of the advantages of this kind of technology is that you can do a single pass of data collection, which is often the most costly part of field data collection. It's not the processing, it's actually getting out into the field. And you can deliver multiple different types of data for multiple groups. So design level data, digital train models of the surfaces. And we can give you automatic break lines at things like edge of pavement or pavement markings or features. Safety data, so the grade of a road, for example, or the cant or crossfall of a railway, or the horizontal curvature or vertical curvature. Foreign object debris, for anyone that's not familiar, that's things sitting on a runway that can be potentially ingested by turbine engines and do damage. All kinds of inventory-related information, how long is the road, how wide is it, and then a whole host of pavement management-related data. Anything and everything you need to manage a road from a functional standpoint, we can capture in one pass automatically. So cracking, roughness, rutting, potholes, texture, on and on. And it's applicable to asphalt, concrete, chip seal, regular concrete, rigid concrete, grooved concrete, and porous pavements. So these are the two different types of data that come from the system. The image on the left is a grayscale image. We've kind of taken a slice out of the 3D data, and we've prepared an image wherein the darker the shading, the further away the feature is. So there's a number of cracks in a road here, and you can see the cracks nice and clearly in the left-hand image. On the right-hand side is an intensity image. It looks like a digital image of the surface, and that's really what it is. What I'd like to point out is that the cracks that are in the left image are also present in the right image, and if you zoom in, you'll see them. But the point is, having that 3D data instead of having just 2D data, I can immediately find 3D features like cracking, and that's really the value add of doing these things simultaneously. Mind you, there are things that are easier to find using the intensity data, so we develop algorithms that look at both types of data. And when we merge these two together and we apply some artificial lighting, we get a nice 3D view of the road. And we add on one further detail here. All of these lines are the automatically detected cracks on this section of road. And the different colors actually correspond to the different widths of cracks. The turquoise-colored cracks in this case, they're about 3 millimeters wide. So you can imagine this vehicle drove down the road at 100 kilometers an hour, and we detected automatically cracks that were about 2 to 3 millimeters and up. Here's another way of looking at the 3D data. This is the end of a railway tie with some bolting. These are all the 3D triangulated points behind the data. So instead of a grayscale image, here's a 3D model. And then here's an intensity image for the exact same section of rail. Okay, so general principle, let's compare it to LiDAR. How does it compare? How's it similar? How's it different? Okay, so LiDAR is a time-of-flight technology, and I'm sure everyone in the audience can explain this better than I can explain it, but basically you're taking a pulse of light, you're sending it out to an object, and you're measuring the time it takes to go to the object and come back. And because we know what the speed of light is, we can calculate that distance. Laser triangulation, as I explained, we're forming a triangle. We have 2 points on the sensor, and we have a point or a line on the surface. LiDAR is an excellent technology for large surfaces where you don't need a ton of point density or a ton of resolution. So you can generate about 400,000 points per second, 200,000 to 400,000 points per second. And in the Z dimension, you get plus or minus 5 millimeters, which is pretty darn good, frankly. It's a good technology for buildings, great technology for seeing intersections, that type of thing. Whereas laser triangulation is much better suited to smaller surfaces where you need a lot of resolution and a lot of accuracy. So if you're trying to detect something like cracks that are a couple of millimeters in size, you can't use plus or minus 5 millimeters to find something that's 2 millimeters. It doesn't work. So we generate about 10 times the amount of points, 45 million points a second instead of 400. And we provide about 10 times the accuracy, so plus or minus half of a millimeter instead of 5 millimeters. LiDAR is also a great technology for long distances. You know, you can put a LiDAR sensor in a plane and drive over a field, no problem, a few kilometers away. We can't do that. We're not going to do that. It's 2 to 3 meters would be our effective range. So I say companion because we have a lot of customers that on the same mobile mapping vehicle use our sensor as well as a LiDAR sensor, and they're looking for different things. LiDAR, you can have a stationary device, you can have a mobile device. Our system only works because the vehicle's moving. It's moving the sensor past the thing that we're scanning. There's nothing that's spinning in our system. Well, picture's worth 1,000 words. Let's look at a few examples. This is what you get with LiDAR of a railway. You can see the railway ties, pretty broad field of view. But if you zoom in, there's not a lot of points on the actual features. This is what you get with our system. It's like walking out to the rail itself. You have all the details. You see all of the ballast material. You can see the fasteners. You can see the rails. And we have all the 3D dimensions of it as well. Roadway intersection, I like this view because you can see a lot of different assets in it, street signs and curb and that kind of thing. But again, not a lot of points on the ground. Okay, so if you're trying to detect cracks in this image, you're out of luck. This is the kind of thing that we can do on pavement. Okay, so bit of a compare contrast. Let's talk about data processing, because that's a bit different too. We don't generate point clouds that someone has to go through and register all the points. That's not our business. Our business is in developing algorithms to automatically detect features, make measurements. So we develop algorithms to look at each different stream of data, sometimes independently, sometimes together. There are some things that are best found with the 3D shape. So things like rutting in a road, or potholes, or railway ties, or rails, those are all things that the 3D shape makes them easy to find. Then there are some things that you really need some other kind of data. They don't have much 3D shape, like pavement markings. They have a bit of a height difference, a bit of a 3D shape, but really we can find them very quickly by analyzing the intensity data. They're very reflective due to the glass beads. Moisture in a tunnel would be another example. But this is where it gets interesting. By combining two different types of data analysis, two different algorithms, we can then find features or characterize features that are really tough to find otherwise. So sealed cracks on a roadway, they don't have any depth because they're sealed. But organizations want to know that they're there, and they want to know how the seals are performing. So the only way to detect that is by having a combination of data. So we look at how reflective the surface is. Seals are pretty reflective. And we look at the smoothness of the surface. The macro texture of the surface are pretty smooth. And then we can bring in other data like inertial data, and we can get things like vertical curvature from it. But again, interestingly, if we combine that with the 3D shape, then we can get things like the roughness of the road by creating an inertial plane. Here's another way of looking at data analysis. The top graph is for 1/2 of a road lane. It's in a wheel path. The bottom graph is the same. The top graph is for range data, 3D data. The bottom graph is intensity. So the first thing we can pull out is a macro texture of the surface. This isn't noise that we're looking at. It's actually the shape of the rocks in the road. Next thing we can see is this long wavelength depression. That's a rut in the road. And in the middle of that rut, we have a crack. And then in the intensity image, you can see we get a fairly nice response from that lane marking. It's very reflective. So you can't really see the lane markings in the 3D. You can't really see any of the 3D features in the intensity. That's the value of having both data streams simultaneously from the same sensor. We have an automated software processing kit, so you can process 10 meters at a time or 10,000 kilometers at a time. It outputs a number of different types of data. Everything from JPEG images, where you get a nice view of the road or the rail or the tunnel, or you get a map of all the cracks, to text reports, so all of the numeric values that go along with these nice drawings of cracks. How long are the cracks? How deep are they? How wide are they? What's the total quantity? And then last but not least, a variety of 3D outputs. We have our own proprietary format, but we can also give you an LAS file, a Bentley microstation file. So here's an example of the type of report that you might get out of the system for something like cracking. You can see we've detected a bunch of cracks, and we've also classified them and severity rated them. So severity has to do with how wide the crack is. Classification has to do with where is the crack and the orientation. Is it transverse to the direction of travel? Is it longitudinal? And is it in the wheel path? So if it's in a wheel path, typically it's related to traffic fatigue. And then here's a corresponding XML data. So for every crack that we draw, every railway tie that we highlight, there's a series of coordinates all the way down into the millimeter level. And then there's a nice example of a Bentley file where we've brought in the 3D profile of the road, we brought in the cracks, we brought in brake lines at the pavement markings. Okay, so we can get really nice images, but if you're traveling at 100 kilometers per hour over a road that's not terribly smooth, it can be pretty challenging. You got a lot of things working against you. You've got vehicle acceleration, deceleration. The vehicle is pitching forward and reverse. It's rolling left and right. You've got centripetal force. We have to compensate for some of this stuff, otherwise we're not going to get very nice data in the real world. So we can bring in some sensors to do that. We can bring in some inertial measurement units to measure the pitch, roll, and heading of the vehicle. We can also get acceleration and gravity. we can bring in an optical encoder. So this is measuring how many times that wheel goes around, and that translates into linear distance. We actually use that to trigger when to capture data. So unlike mobile LiDAR, in many cases, when you stop the vehicle, LiDAR is still collecting. We don't do that. When you stop the vehicle, we stop collecting. You can plug GPS into the system as well to tie everything back to the real world. Of course, now I kind of have another problem because I've got a whole bunch of additional coordinate systems by these different streams of data. I've got GPS coordinates, I've got linear coordinates, I've got IMU data, I've got 2 different sensors. So how do I tie all this stuff back together? So one of the first things we do is when we install an IMU, we align it with the laser. So there's no lever arm between having an IMU or an inertial navigation system somewhere else in the vehicle. But I have 2 sensors, so I've got to do something about that. Okay, so we have a calibration object that we use. This is a precision machined object. We know all of the dimensions, we know all of the angles. If we set that down on a road, or between rails or some other surface we want to scan, we can then drive over top of it and get that same object scanned simultaneously by both of the sensors. And that allows us to align the left and right sensors and establish a relationship between the 2. So here's a 3D scan. It's a little tricky with the lighting here, but what I'm looking for is a nice aligned image in the middle. I want to see this pavement marking look nice and uniform, and I want to see this calibration object look nice and uniform. I don't want to see weird shapes coming out, and as you can see, it is really nicely aligned. This is an automated process, but this is part of the mix. The other thing I need to do is I need to bring my linear distance and my IMU coordinates together. We have an automated process for that as well. Okay, so then we can go into the field. We can make a number of reference points in the field and perform repeat runs on those points and look at the repeatability of the derived location of those points from our sensors. So we can look at that on a 4-meter section, or we can look at it on a longer section closer to 70 or 80 meters and do repeat runs. And if we look at just the inertial data on a 4-meter section, as you can imagine, it's going to look really good. It's only 4 meters. It's pretty hard not to get that right. So you can see multiple scans here. You can see, for example, scan number 2, it's 2.28 millimeters, 3.06 millimeters within actual, and then 4.51 for the Z. So the mean error here is about 3.66 millimeters. Now, if I go over a longer section, 84 meters, something starts to happen. I'm still doing quite well in the X and Z, 2.94, 3.65, but the Y, longitudinally within the direction of travel, the road is totally out of whack. It's 25 millimeters almost. Okay, why is that? Well, the optical encoder that's used to measure wheel revolutions, it's very susceptible to things like inflation changes, the wheel slipping free of the road, bumps in the road, driver wander. There's all kinds of reasons why that type of data can be less accurate. So if I bring in a couple of surveyed points from a total station or traditional survey, 4 meters, it's not going to make it much better. It's going to tighten it up a little bit from 3.66 to 3.3. But this is where it's going to make all the difference on my longer section, this 84-meter section. You can see that I'm going to get a mean of 4.17 instead of 12 in the other one. And it's, you can point right at the Y. Y is now 3.72 millimeters. Okay, why does all this matter? What's the point of all this? The point is, if you drive over something like this with a 3D scanner, this speed bump, you're going to have all kinds of strange stuff happening in the profile because the sensors are going to get closer to the pavement surface and then farther away, closer. That's going to make a wave in your data that's not really there. And you can kind of see it at the edge of the pavement here on the left-hand side. There's some waves in this pavement. Well, they're not actually there in real life. So if we take that inertial data and we correct it, we can smooth out that profile and give you a real representation of the road. Here's another example. There's some transverse cracks here that as you go over the transverse cracks, if you look at the line in the left-hand side, you can see there's some weird waves in there. That line is not really like that in real life. This is what the line looks like in real life. You can see we've added in here the vertical and the horizontal curvature as well, provide a proper representation of this road. And then as a last step, we can add in other things, different features that have been detected and displayed. And that concludes my talk. Thank you very much.